Welcome to This Explainer. Today, we're diving into the extreme industrial engineering required to bottle one of the most ubiquitous chemicals on the planet. You might think pumping liquid into a plastic jug is a pretty straightforward gig, right? Well, when you're dealing with massive volumes of highly concentrated agricultural chemicals, it is anything but simple. Just to wrap our heads around the sheer scale of this challenge, look at the global footprint. In 2024 alone, a staggering 209.8 million hectares of genetically modified herbicide-tolerant crops were planted worldwide. That is an astronomical amount of land. And that demand? That's exactly what drives this massive, multi-billion-dollar agrochemical industry that literally has to run around the clock just to keep up.
But here's the thing. Long before these chemicals ever make it to a farm, industrial engineers have to solve an absolute nightmare of a puzzle. I mean, think about it. How do you safely package a chemical that can literally eat right through solid metal and generate explosive gases while doing it? It takes a crazy delicate balance of chemistry, fluid dynamics, and metallurgy to pull it off.
So, let's jump straight into Section 1, the chemistry of weed control.
To figure out how to package this stuff properly, we really need to understand how it's built from the ground up. In its raw form, glyphosate is just a weak acid, and it actually doesn't dissolve very well in water. So, to whip up a super-concentrated liquid, chemists have to neutralize it with an alkaline base, which turns it into a soluble salt. Now, you'll often see active ingredient on a label, which includes the heavy weight of that salt, but the acid equivalent? That's what measures just the parent acid. That's the actual weed-killing muscle. And since different salts have totally different weights, engineers absolutely rely on that acid equivalent to standardize their concentrations and properly calibrate all the packaging machinery.
All right, moving on to Section 2, battling the foam crisis.
See, the raw herbicide by itself just rolls right off a plant. So, to make this chemical actually stick to and penetrate a waxy leaf, engineers pump it full of aggressive surfactants, which, if we're being honest, are basically just heavy-duty soaps. But this leads to our very first industrial headache, the foam crisis. Imagine pumping a liquid loaded with soap into a bottle at incredibly high speeds. It traps air, instantly. This creates these really persistent, thick foams that just overflow the containers, totally mess up the dilution ratios, and bring production line speeds to a grinding halt. You're left with uneven dosing, massive product waste, and just a terribly sticky, hazardous mess all over the factory floor.
So how exactly do they fix that mess? Well, the chemical solution is to introduce highly active defoamers like Invino 2200, and this right here perfectly showcases the sheer magic of chemical engineering. I mean, they use a microscopic 0.05% dose of this stuff. That tiny drop immediately migrates straight to the bubble walls, kicks out the surfactant, and instantly collapses the whole foam structure. And it does all of this without ruining the actual weed-killing power of the herbicide. It's wild.
But relying on chemistry alone just doesn't cut it. Engineers need a mechanical fix too. Your traditional volumetric piston fillers just push a preset volume of liquid into a bottle. But if that liquid is secretly half full of microbubbles, the actual amount of chemical the customer gets is going to vary wildly. So, mechanically, modern packaging plants use electronic net weight filling. It is an absolutely ingenious method. They put individual load cells under every single bottle to measure the exact mass of the liquid, completely ignoring any of that remaining foam or trapped air. Problem solved.
Which brings us to Section 3, the metal-eating monster.
Now, even if you entirely eliminate the foam, the liquid itself is incredibly destructive to the very machinery trying to bottle it. Honestly, it's the kind of thing that keeps process engineers up at night. Glyphosate is what we call a powerful chelator. That means it has these molecular donor groups that basically act like homing missiles, actively seeking out and binding to metal ions. So if this stuff is just sitting inside a standard stainless steel pipe, it is actively ripping transition metals, like iron and chromium, right out of the protective layers of the steel. It accelerates localized pitting and literally eats the machine from the inside out.
And oh, it gets so much worse. Let's say this chemical accidentally touches galvanized steel. The acidic protons will drive this rapid redox reaction that dissolves the zinc coating and releases highly flammable hydrogen gas. Think about that for a second. If that's happening inside a closed storage tank or some unvented piping, you're looking at a severe, catastrophic explosion risk for the entire facility, especially if a tiny spark of static electricity happens to go off anywhere on that packaging line.
So, the big takeaway here is that to survive this metal-eating monster, engineers are forced to build these processing lines out of some very specific, high-end materials. Basic carbon steel, galvanized steel, completely off the table, forbidden. Instead, these plants have to use low-carbon 316L stainless steel, heavily dosed with molybdenum, just to fight off that pitting. And for all the dynamic seals and hoses, they rely on pure titanium and super high-tech inert plastics like PVDF and PTFE.
All right, on to Section 4, Precision Packaging and Safety. Okay, so you've built machinery that won't melt or blow up. Great. Now engineers have to focus on protecting the plant operators and the end consumers. Because these formulations are packed with irritating surfactants and super-concentrated chemicals, they are heavily regulated. The EPA actually mandates strict child-resistant packaging for any of the smaller residential products. Manufacturers have to pass rigorous, real-world testing to prove that kids under 5 literally cannot pry these bottles open. To pull this off consistently, plants use these highly specialized capping machines that apply an insanely precise, digitally verified torque to every single safety cap on the line.
And then there's the labeling. The sheer volume of legally required text, we're talking safety warnings, environmental hazards, endless dosage tables, there is absolutely no way it's all fitting on a standard bottle sticker. So factories are forced to use these massive 40-page fold-out concertina booklet labels. Yeah, 40 pages. Just trying to glue a thick mini-book to a curved plastic jug moving at lightning speed requires custom, servo-driven wraparound machinery. They actually have to use heavy pneumatic rollers to squeeze out every single air bubble just to make sure the peel and reseal border lays down perfectly flat.
Let's slide right into Section 5, Cleaning and Compliance. So once a massive batch is totally done, you can't just hook up a garden hose and rinse the system out. If you leave even a microscopic trace of this systemic weed killer hiding inside a pipe, it could catastrophically contaminate the next product they run and destroy an entire harvest. No joke. To prevent that kind of disaster, these facilities deploy a massive, fully automated 5-step clean-in-place, or CIP cycle. It is wild to watch. They start by firing a physical rubber plug, which they call a pig, straight through the pipes using blasted compressed air to shove out all the bulk liquid. After that, they run a boiling hot caustic wash just to melt away those sticky surfactants, and finish the whole thing off with a neutralizing acid wash to derouge and restore the steel's protective oxide layer. It is essentially a perfectly choreographed chemical ballet.
And finally, Section 6, a booming global market.
This incredible gauntlet of intense engineering, exotic metallurgy, and automated chemistry, it's not just some fun exercise in science. It is the absolute backbone of a colossal, rapidly changing global economy. If we look at the breakdown of global consumption, Latin America is definitely leading the pack. And that's largely driven by these massive zero-tillage soy and corn operations down in Brazil and Argentina, where chemical weed control completely replaces mechanical plowing to save on soil moisture. Meanwhile, North America is a highly mature, saturated market. But the Asia-Pacific region, that's where we are seeing the absolute fastest global growth, mainly because manual labor costs are rising and agricultural modernization is accelerating so quickly over there.
Driven almost entirely by the endless planting of genetically modified, herbicide-tolerant crops across all these regions, the global market valuation for glyphosate hit an estimated $13.5 billion by 2025. That is a massive financial incentive, and it pretty much guarantees that these packaging lines are going to be pushed to run faster, safer, and with even tighter precision in the years to come. But as we all know, nature always adapts. With weeds naturally developing resistance out in the fields, chemical companies are already being forced to blend even more volatile, multi-chemical stacked trait herbicides. Mixing glyphosate with other super-aggressive agents is going to create entirely new thermodynamic and corrosive nightmares for this processing equipment. Which leaves us with one incredibly provocative question. As these formulations get exponentially more complex and way more corrosive, how on earth will industrial engineering adapt to safely bottle the extreme chemical combinations of the future? Something to think about. Thanks for hanging out with me for this explainer, and I will catch you guys in the next one.